So this is 7.3 beta, and we're going to come back to the Google Slides. Most population distribution are not normal. Yeah, exactly. So look what they've got here. We've got this picture where here's the parent population. This parent population is uniform. Yes. This parent population in the middle column is skewed right. In the third column, bimodal. So you take these means. So if the mean was size, if all your sample size was size 2, and you plotted those means, what would happen? Well, this would be symmetric. This would take on the same shape, the skewness. Okay, and this thing, these means, when you average these two in the right column, will give you a distribution in the center, and you might end up with 2 to the right or 2 to the left. But if you take a sample size of 25, this doesn't make it criteria 30, but as the sample size gets larger, you see how symmetric the distribution is. So that's the idea. The central limit theorem says the distribution of all those x bars will be approximately normal if your sample size is greater than or equal to 30. If the original thing was normal, then it doesn't matter. It doesn't have to be 30. So here's an example. The distribution is skewed right. The center is 30 and the step is 20. You take 40 current customers. So your sample size is 40. And he's going to budget 35 minutes per customer to complete the work. Is that going to be enough? Well, think about this. He's going to budget 35 minutes. Why? Because it's 30 minutes is the center. He's giving himself 5 minutes extra time. But the step's 20 minutes. So they're going to have everything to the right of 35 would be a problem if he budgets this. So the sample size is large enough. Here's the step. We good? Here's 35 over here. That's what he budgeted. So everything to the right of that is bad news because they're the customers that he would anticipate would take longer than 35 minutes for the oil change. Well, then, he should budget 40 minutes. Yeah, but then he's going to fit less customers in. Does that make sense? Like he's trying to maximize the people who get in there and minimize the waste. So what does that tell you? Well, if you do normal CDF, it's telling you a little less than 6% of the customers would go over the 35 minutes, which is like 1 in 19, 1 in 18. Well, if you decide that's not good enough, you can work backwards. You decide how many customers that you can expect to go over the time and work from that way instead of arbitrarily saying we're going to pick 35 minutes. Okay? How much time should he be? If he wants to be 99% certain he doesn't go to a budget. Well, that's going the other way. So he wants to be 99% certain. And the area of the curves, ready? Area to the left here is 99%. So what's that z-score? And then translate to a data point. 37.4 minutes. Now, if he said, I'm going to give 37.4 minutes in my calendar, then he'd be 99% certain that he could do the oil change and stay on budget, time budget. So here's what's going on. We talked about in the alpha lesson the center and spread of the sampling distribution of X bar. In the beta lesson, the shape of the sampling distribution. If the population is normal, then the shape of the distribution of X bar will be normal. If the population is skewed and your sample size is at least 30, then the shape of the distribution of X bars will be approximately normal. So I just kind of summarized this here and said, okay, how about the distribution of proportion, 7-2, and means 7-3? Because we're sampling without replacement, the condition is the population has to be greater than 10 times the sample size. When you get to the AP test, right? When you get to an inference question, you have to answer a question, you're going to have to list the conditions. If you draw a blank or you're nervous or whatever, you just literally write this. The sample is less than 10% of the population, because that's going to be the condition for both proportions and means. Now what? But you want this to be approximately normal. If it's a proportion, 10 times p hat's got to be greater than equal to 10. 10 times 1 take away p hat's got to be greater than equal to 10. If it's a mean, 10 has to be greater than equal to 30. That was what was in today's lesson. Okay? So we're going to pause the video, and you're going to go to two problems, 63 and 67. For 63, and again, it's the same data set as yesterday about the songs on the iPod. If you take a sample of size 5, right, the population distribution is skewed to the right. So you have these outlier songs that are really long. If the sample distribution is 5, you expect the sampling distribution of size 5 of those means to be skewed right. If the sample size is 100, that's going to make your sample distribution of sample means approximately normal. Make sense? The picture looks like this. It's skewed right. These songs. But if you took 100 of these songs, you're going to have some songs out here, but the sample size is so large that your mean is likely to be more here. And you're going to paste all these means each time with the sample size of 100, it's going to go to the approximate normal. And 67 is a different data set. So you're saying the expected value from this picture is 1.6 flaws. Well, the question asks, if you took 1 square yard of material, or take 50 square yards. Well, 1 or more flaws, right? 1 flaw is here. Or so, I'm sorry, 2 flaws. is over here to the right, yes, it's more likely in a smaller sample size. But you're separating yourself from the center, which is 1.6. B asks, what's the matter with the first one? Well, one's not big enough for this to be approximately normal. And then C asks the second event. So the second event is, the step was, in the question, 1.2. So if you had a sample size of 50, then the step would be this. More than 2 flaws. 2 to the right. I just did normal CDF, go from 2, and I made 100, an arbitrary large number to the right. With the center's 1.6, and this is the new step, and that's about 1%, a little less than 1% chance that if you had a sample size of 50, that you would find an average of 2 or more flaws, an average of 2 flaws. Okay? So I want to come back to 2 things in summary, and those are here on the PowerPoint. So this is the picture from yesterday about the heights of girls. And this is the population. We showed you this yesterday, but it's important to come back to this. This lower curve is the population. So the step was given. But when you take a sample size of 10, then you're dividing the step of the population by root 10. So the step gets smaller. And the data is going to be more compact. It's harder to separate an average of 10 girls' heights from the center than it is to separate 1 girl's height from the center. And then the other slide we want to deal with is this, about the symbols, right? There's 10 symbols there on that slide. It's kind of like we say to you, I don't know, what's the definition of R squared? No one? It's the proportionate change in the output that you attribute to change in the input. Same thing with these 10 symbols. They have to make sense to you. Like, this is the language of the course. So you got this slide where it's sitting here. P hat through sigma of x bar. Like, how many of those 10 can you identify what they mean? You need to do this. You need to write it down, then write it down. We're going to go through. P hat is the sample proportion. X bar is the sample mean. N is the sample size. P is the parameter proportion. It is the true proportion. That's why I called your attention to that problem on the math type of the PDF. There's a difference between P and P hat. Mu is the population mean. Sigma is the population step, the spread. All that is pre-chapter 7. The last word from chapter 7, U of P hat is the center of the sampling distribution of sample proportions. Sigma P hat is the step for that distribution. U of X bar is the center of the distribution of sample means, and sigma of X bar is the step of that distribution. So, if you are at home, doesn't matter whether you're AVP or you're an HL, you're leaving to go to College Board to do the exit ticket. Okay? So we will see you in the building on Thursday.